Welcome to Sleepy Science Student, where we explore the wonders of the universe one gentle concept at a time. Tonight, we're going on a slow, peaceful journey into one of the most fascinating constants in all of physics, the speed of light. It's a topic that touches everything from the way we see stars in the night sky to the very structure of space and time itself. I hope this video isn't too interesting. Though, if it does happen to keep you awake, at least you'll be learning something remarkable about the universe's ultimate speed limit in the process. Not the worst way to spend a sleepless night. Before we drift into the realm of photons and cosmic velocities, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this quiet little channel grow and means more curious minds can find their way here to learn and relax. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in Berlin at midnight, or listening from a hammock in Santiago at 3 hours in the afternoon while the sun streams through your window? Let me know in the comments. It's always such a joy to see the sleepy science community scattered gently across the globe, all pondering the same beautiful mysteries together. Now, settle in, get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you, like gentle moonlight filtering through your window. Let your shoulders relax. Let your breathing slow down. And as we begin this gentle voyage into the nature of light and speed, remember this video is for educational and relaxation purposes only. It's not intended as medical advice, professional consultation, or a replacement for actual sleep hygiene, though speaking kindly to photons is always encouraged. Ready? Let's begin. What is the speed of light? Let's start with something beautifully simple. The speed of light, often written as the letter c in physics equations, is approximately 299,792,458 meters per second. That's about 300,000 kilometers per second, or if you prefer, roughly 186,000 miles per second. It's the fastest anything can travel in our universe as far as we know. But what does that number really mean? Numbers can be so abstract, so distant from our everyday experience. When we say light travels at 300,000 kilometers per second, we're describing something almost incomprehensibly quick. In the time it takes you to blink your eye, about 100 milliseconds, light could travel around the entire Earth 7.5 times. Let that sink in gently. 7.5 times around our planet in a single blink. Imagine you're standing on a beach at sunset, watching the light dance across the waves. That light left the sun about 8 minutes and 20 seconds ago. It traveled through the vacuum of space, crossing roughly 150 million kilometers, just to reach your eyes at this peaceful moment. The light touching your face right now is, in a sense, 8 minutes old. It's a traveler from the recent past, a gentle messenger carrying warmth and information across the cosmic ocean. Light doesn't just move quickly, it moves at exactly the same speed regardless of circumstance. Whether it's traveling through the emptiness of space or racing from a flashlight you're holding in your hand, light always moves at this constant velocity. It's one of the universe's most elegant rules, a speed limit that nothing with mass can ever reach, let alone exceed. Think of it like this. If you could somehow catch a ride on a beam of light, which you can't, but imagine for a moment, time itself would stop for you. You'd exist in a strange, frozen moment where the entire journey happened instantaneously from your perspective. For everyone else watching, of course, you'd still be moving at that tremendous speed, taking time to travel from place to place. But for you, riding that impossible beam, the universe would be fundamentally different. Right now, as you lie there, light is bouncing off every surface in your room. It's reflecting from your walls, your ceiling, your furniture. It travels from these surfaces to your eyes in mere nanoseconds, billionths of a second. The entire visible world around you is being constantly repainted by light, moving at this incredible speed, fast enough that everything seems continuous and solid, rather than the flickering, bouncing phenomenon it truly is. The speed of light is not just a random number that happened to be measured. It's woven into the very fabric of space-time itself. It appears in equations describing electromagnetism, in Einstein's famous EMC2, in the relationships between space and time. It's a fundamental constant of nature, as basic to the universe as the existence of matter or energy. Scientists often refer to the speed of light with a curious kind of reverence. It's not just fast, it's the fastest. It's not just a speed limit, it's the cosmic speed limit. Nothing can carry information or causality faster than light. If you could somehow send a signal faster than light, you'd be violating not just physics, but the very concept of cause and effect. You'd be creating paradoxes, backward-flowing time, impossible contradictions. But why? What makes this particular speed so special? Why isn't the cosmic speed limit 400,000 kilometers per second, or 200,000, or some other number entirely? The answer, interestingly, is that the speed of light falls directly out of the properties of space itself. It's related to something called the permittivity and permeability of free space, essentially, how much electric and magnetic fields can permeate the vacuum of space. When James Clerk Maxwell unified the theories of electricity and magnetism in the 1860s, he discovered something remarkable. His equations naturally produced a wave that propagated through space, and when he calculated the speed of this wave using the known values for these electrical and magnetic properties of space, out popped a number very close to the measured speed of light. It wasn't a coincidence. Light is an electromagnetic wave, and its speed is built into the structure of electromagnetic theory itself. Let's pause for a moment here. Take a breath. Feel the weight of your body against your bed or chair. You are, right now, being bathed in light of various kinds. Visible light if you have lights on. Infrared light from the warmth of your own body. Radio waves from distant transmitters. All of it traveling at exactly the same speed. All of it following the same cosmic rules. The speed of light creates what we might call the pace of the universe. It determines how quickly information can travel, how quickly events in one place can influence events in another place. When you look up at the night sky, you're not seeing the stars as they are now. You're seeing them as they were when their light began its journey. The nearest star system, Alpha Centauri, is about 4.37 light-years away. That means the light you see from it tonight left those distant suns more than 4 years ago. And this gets even more dreamlike when you consider distant galaxies. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. The light from Andromeda that enters your eye on a clear night began its journey before modern humans had even evolved on Earth. You're seeing ancient light, preserved perfectly, still carrying information about stars and gas clouds that existed in the distant past. In a sense, the speed of light gives the universe a kind of gentle lag, a built-in delay between event and observation. Cause and effect are separated by this cosmic speed limit. If the sun suddenly vanished right now, which it won't, but imagine, we wouldn't know about it for 8 minutes and 20 seconds. For that brief window of time, we'd still see the sun, still feel its warmth, still orbit around something that no longer existed. This might sound unsettling, but there's something oddly peaceful about it. The universe moves at the pace it moves. Light takes the time it takes. Everything unfolds according to these deep mathematical rules that have existed since the beginning of time itself. There's no rushing, no hurry. Just the steady, constant flow of photons through space at 299,792,458 meters per second. Some scientists like to point out that the speed of light isn't just about light. It's really the speed of causality, the speed of cause and effect. If you could somehow make gravitational waves, or send quantum entanglement signals, or use any other method to transmit information, you'd find that the maximum speed is always the same. It's c. Always c. The universe has this fundamental speed limit built into its very nature. Measuring the unmeasurable. Now, here's a curious question that might drift through your mind. How did anyone figure out how fast light travels in the first place? After all, 300,000 kilometers per second is so fast that light seems instantaneous in most everyday situations. When you flip a light switch, the room illuminates so quickly that there's no perceptible delay. So how did scientists measure something that appears to happen in no time at all? The story of measuring light's speed is a gentle tale of human curiosity and increasingly clever methods. It's a journey that spans centuries, from early philosophers who wondered if light traveled at all, to modern scientists who can measure its speed with exquisite precision. The ancient Greeks had mixed opinions about light's speed. Some, like Empedocles, believed that light must take some time to travel. Others, including Aristotle, argued that light transmission was instantaneous. After all, when the sun rises, doesn't the entire landscape illuminate at once? There's no visible wave of light creeping across the land, no perceptible delay between the sun appearing and the world brightening. For many centuries, this question remained in the realm of philosophy rather than experimental science. How could you possibly measure something so fast? You'd need a method that could detect incredibly tiny intervals of time. Or you'd need to observe light traveling vast distances, where even a tremendous speed would result in a measurable delay. The first serious scientific attempt to measure the speed of light came from Galileo Galilei in the early 1600s. His method was charmingly direct, if ultimately unsuccessful. He and an assistant stood on hilltops about a mile apart, each holding a shuttered lantern. Galileo would uncover his lantern, and when his assistant saw the light, the assistant would uncover his own lantern. Galileo would then try to measure the time between uncovering his lantern and seeing the light from his assistant's lantern. You can probably guess why this didn't work. Light travels so quickly that it covered the distance between the two hills essentially instantaneously. What Galileo was really measuring was human reaction time, the delay while his assistant processed the visual signal and responded. Still, it was a beautiful attempt, a simple experiment that showed the scientific spirit of trying to measure the universe. The first successful measurement came from an unexpected source: astronomy. In 1676, a Danish astronomer named Ole Rømer was studying the moons of Jupiter, carefully timing their orbits. He noticed something peculiar. When Earth was moving toward Jupiter in its orbit, the eclipses of Jupiter's moons seemed to happen slightly earlier than predicted. When Earth was moving away from Jupiter, the eclipses seemed to happen slightly later than predicted. Rømer realized what was happening. It wasn't that the moons were speeding up and slowing down. It was that light took time to cross the changing distance between Earth and Jupiter. When Earth and Jupiter were closer together, the light from Jupiter's moons had a shorter distance to travel, so the eclipses appeared to happen earlier. When they were farther apart, the light had to travel farther, creating a delay. By measuring these variations over the course of Earth's orbit, Rømer was able to calculate an approximate speed for light. His value was about 220,000 kilometers per second, not exact by modern standards, but remarkably close given the limitations of 17th century measurements. For the first time, humanity had put a number to one of the universe's fundamental constants. Think about how clever this method was. Rømer used the solar system itself as his laboratory, with Earth and Jupiter as the endpoints of his measurement. He turned the vast distances of space, which had previously made measurements seem impossible, into an advantage. The greater the distance, the more noticeable the light travel delay became. Over the next 2 centuries, other scientists refined this measurement using various astronomical observations. In 1728, James Bradley used observations of stellar aberration, a slight apparent shift in star positions caused by Earth's motion, to calculate a speed of light close to 301,000 kilometers per second. The pieces were slowly coming together, like a puzzle assembling itself across generations. But the real breakthrough in terrestrial measurements came in the mid-1800s. French physicist Hippolyte Fizeau developed an ingenious experiment in 1849. He set up a rapidly rotating toothed wheel with a light source on one side. The light would pass through a gap in the wheel's teeth, travel about 8 kilometers to a distant mirror, reflect back, and return to the wheel. If the wheel was rotating at just the right speed, the light would pass through one gap on the way out and return through the next gap. By adjusting the rotation speed and measuring when the returning light could pass back through the wheel, Fizeau could calculate the speed of light. His result? About 313,000 kilometers per second. Getting closer. Léon Foucault improved on Fizeau's method just a year later, using a rotating mirror instead of a toothed wheel. He got even more accurate results. Each generation of scientists built on the work of the previous generation, steadily refining the measurement, narrowing in on the true value like a gentle, persistent tide. By the late 1800s, the speed of light was known to about 5 significant figures. American physicist Albert Michelson became almost obsessed with measuring it more and more precisely. Between the 1880s and 1920s, he conducted increasingly sophisticated experiments, eventually using mountaintops in California as measurement points. His final measurement, conducted in 1926, gave a value of 299,796 kilometers per second, less than 4 kilometers per second away from the currently accepted value. Let's pause again. Imagine these scientists working across centuries, each adding their small piece to humanity's understanding. Galileo on his hilltop with a lantern. Romer staring through his telescope at Jupiter's moons. Fizeau carefully adjusting his rotating wheel. Michelson shuttling light between mountaintops. Each of them driven by the same curiosity, the same desire to measure something that seemed immeasurable. The modern definition of the meter is actually based on the speed of light rather than the other way around. In 1983, the international scientific community decided to define the meter as the distance light travels in exactly 1,299,792,458 of a second. This means the speed of light is now an exact defined value, 299,792,458 meters per second, with no uncertainty. We've essentially locked in the speed of light and defined our distance measurements around it. Why would scientists do this? It's because measuring time has become more precise than measuring distance. We have atomic clocks that can measure time intervals with extraordinary accuracy. By defining the meter in terms of light travel time, we've tied our spatial measurements to our most precise temporal measurements. It's an elegant solution, a way of anchoring our measuring systems to the fundamental constants of the universe. So when you think about the speed of light now, remember that it's not just a measured quantity anymore. It's a defined constant, a number we've chosen to use as a foundation for our system of measurements. The meter itself is now defined by light speed. In a sense, every time you measure distance with a meter stick or a ruler, you're using the speed of light as your ultimate reference. This journey from Galileo's hilltop experiment to modern laser measurements spanning the entire Earth reminds us of something gentle and profound. Knowledge accumulates slowly. Understanding builds over time. Each generation contributes what it can, and eventually, through persistence and cleverness, we uncover the universe's secrets. There's no rush, just the steady, patient work of curious minds asking questions and seeking answers. Why is the speed of light the limit? Now we come to one of the most fascinating aspects of the speed of light. Why nothing can travel faster than it. This is where physics becomes almost philosophical, where the rules of the universe start to reveal a deeper logic that's both beautiful and strange. The answer lies in the work of Albert Einstein and his theory of special relativity, published in 1905. Einstein started with 2 simple postulates, 2 basic assumptions about how the universe works. The first was that the laws of physics are the same in all inertial reference frames. In other words, whether you're standing still or moving at constant velocity, the universe behaves the same way. The second postulate was that the speed of light is constant for all observers, regardless of their motion. That second postulate might seem innocuous, but it has profound implications. Think about it for a moment. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, an observer standing on the platform will see the ball moving at 150 kilometers per hour, the sum of the train's speed and the ball's speed. Velocities add. That's our everyday experience. But light doesn't work this way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, the light doesn't move at 1.5 times the speed of light. It moves at exactly the speed of light. Someone standing still will measure the same speed for that light beam. An observer on a different spaceship moving in a different direction will also measure the same speed. Light always travels at c, no matter who's watching or how they're moving. How can this be? It seems to violate common sense. And here's where Einstein's genius comes in. He realized that for the speed of light to remain constant for all observers, something else has to change. That something is space and time themselves. When you move very fast, approaching the speed of light, time slows down for you relative to someone who's stationary. This is called time dilation. The faster you go, the more pronounced the effect. If you could somehow travel at 99.9% of the speed of light, time would pass about 22 times slower for you than for someone at rest. You might experience 1 year while decades pass on Earth. Similarly, distances contract in the direction of motion. This is called length contraction. If you're traveling at a significant fraction of the speed of light, the distance to your destination actually becomes shorter from your perspective. The universe itself seems to compress in the direction you're traveling. These aren't illusions or tricks of perception. They're real, physical effects that have been confirmed in countless experiments. Particles called muons, created in Earth's upper atmosphere, should decay long before reaching the ground based on their known lifetimes. But because they're moving at such high speeds, time dilation extends their lifetimes from their own reference frame, or equivalently, the thickness of the atmosphere they must traverse is contracted, allowing them to reach the surface. We can measure this. We can observe time dilation and length contraction directly. Now here's where the cosmic speed limit comes in. As you accelerate and approach the speed of light, something interesting happens to your mass, or more precisely, to your momentum and energy. The faster you go, the more energy is required to accelerate you further. It's not a linear relationship, it's exponential. Imagine pushing a boulder up a hill that gets steeper and steeper the higher you go. At first, it's hard but manageable, but as you climb, the slope increases. Soon, it's almost vertical. Eventually, it would become completely vertical, an infinite slope that no amount of pushing could overcome. That's what happens as you approach the speed of light. The amount of energy needed to accelerate you increases dramatically. To actually reach the speed of light would require infinite energy. And since the universe doesn't have infinite energy to give, nothing with mass can ever reach this speed. The speed of light becomes an asymptotic limit, something you can approach but never quite reach. Only things without mass, like photons, the particles of light itself, can travel at the speed of light. And interestingly, they can't travel at any other speed. Photons are born moving at c, and they continue at that speed until they're absorbed by something. They never accelerate, never decelerate, never stop. There's something almost poetic about this. Light doesn't experience time the way we do. From a photon's perspective, if we can even speak of such a thing, its entire journey happens instantaneously. It's emitted and absorbed in the same moment. All of its existence occurs in a single, eternal now. The universe is a different place when you're a photon. But what if you tried to go faster than light anyway? What if you had some exotic method, a warp drive, a wormhole, some physics we haven't discovered yet? Well, here's where things get truly strange. Traveling faster than light wouldn't just be difficult or energy intensive. It would violate causality itself. Causality is the principle that causes precede effects. You drop a glass and then it breaks. You don't see it break and then drop it. Cause comes before effect. This seems obvious, fundamental, almost too basic to state. But it turns out that this ordering of cause and effect is intimately connected to the speed of light. If you could send a signal faster than light, you could potentially send it backward in time from certain reference frames. This creates paradoxes. You could receive a message before it was sent. You could affect events in your own past. The whole structure of causality would break down. The universe would become a tangled mess of contradictions. Think of the speed of light as the universe's way of keeping everything orderly, of making sure that cause always comes before effect, that the future flows from the past in a logical sequence. It's not just a speed limit on motion. It's a speed limit on causality, on information, on how quickly events in one place can influence events in another. Let's rest here for a moment. Breathe slowly. The speed of light is woven so deeply into the fabric of space and time that it defines the structure of reality itself. It determines how fast information can propagate, how causality works, how time and space relate to each other. It's not arbitrary, it's fundamental. And yet, for all its importance, the speed of light is also profoundly limiting. It means that vast portions of the universe are essentially unreachable. The nearest star beyond our sun is over 4 light-years away. Our galaxy is about 100,000 light-years across. The observable universe extends for about 46 billion light-years in all directions. Even at the speed of light, crossing these distances would take unimaginable amounts of time. Some scientists dream of finding loopholes. Perhaps spacetime itself could be warped or folded, allowing shortcuts that don't technically involve moving faster than light through space. Perhaps wormholes exist, tunnels connecting distant regions of the universe. Perhaps there are other dimensions we could travel through. These ideas remain speculative, residing in the realm of theoretical physics and science fiction. But they reflect a deep human desire to transcend limits, to explore beyond the boundaries nature seems to impose. For now, though, the speed of light remains our cosmic speed limit. It's a fundamental feature of the universe we inhabit, as basic as the existence of space and time themselves. And there's something comforting in that. Something peaceful in knowing that the universe has rules, deep mathematical principles that govern how everything works. The speed of light is one of those rules, elegant and unyielding, a constant presence in every corner of the cosmos. Light as a wave and a particle. To truly understand the speed of light, we need to explore what light actually is. And this is where things become wonderfully strange, where physics reveals a duality that challenged and ultimately transformed our understanding of reality. For much of scientific history, there was a debate about the nature of light. Some scientists, including Isaac Newton, believed light was made of particles, tiny corpuscles that traveled through space. Others, including Christian Huygens and later Thomas Young, argued that light was a wave, similar to ripples on water or sound waves in air. Both sides had good evidence. Light seemed to travel in straight lines and cast sharp shadows like particles would. But light also diffracted around edges and produced interference patterns, like waves do. For over 2 centuries, physicists argued about which view was correct, with evidence accumulating on both sides but no clear resolution. The wave theory gained significant support in the early 1800s when Thomas Young performed his famous double-slit experiment. He shined light through 2 narrow slits and observed the pattern that formed on a screen behind them. Instead of 2 bright bands, which you'd expect if light were particles going through one slit or the other, he saw multiple alternating bright and dark bands, an interference pattern characteristic of waves. When 2 waves meet, they can interfere with each other. If the crests of 2 waves align, they add together, creating a brighter region. If a crest meets a trough, they cancel out, creating a dark region. This is exactly what Young observed with light. The light waves coming through the 2 slits were interfering with each other, creating the distinctive pattern on the screen. This seemed to settle the matter. Light was a wave, and when Maxwell unified electricity and magnetism and showed that light was an electromagnetic wave, an oscillation of electric and magnetic fields traveling through space, the wave theory appeared triumphant. But then, in the early 20th century, things became complicated again. New experiments showed that light sometimes behaved like particles after all. The photoelectric effect, where light can knock electrons out of metal surfaces, only made sense if light came in discrete packets of energy, quanta or photons. Einstein won his Nobel Prize for explaining this effect, showing that light energy comes in little bundles, each with an energy proportional to its frequency. So which is it? Is light a wave or a particle? The answer, wonderfully and frustratingly, is both. Light exhibits wave-particle duality. Sometimes it behaves like a wave. Sometimes it behaves like a particle. What it looks like depends on what kind of experiment you're doing, what questions you're asking of nature. This might sound like nonsense. How can something be both a wave and a particle? Waves are spread out. Particles are localized. Waves interfere with each other. Particles collide. These seem like contradictory properties. And yet, experiments force us to accept that light possesses both aspects. Imagine light as a shy creature that shows different faces depending on how you approach it. Ask it to diffract through a narrow opening, and it reveals its wave nature, bending and spreading. Ask it to interact with a single atom, and it reveals its particle nature, arriving as a discrete, localized photon, carrying a specific amount of energy. The speed of light, our constant c, applies equally to both these aspects. Whether you think of light as electromagnetic waves propagating through space, or as a stream of photons, they all travel at exactly the same speed. A photon doesn't accelerate or decelerate. It moves at c from the moment it's created until the moment it's absorbed. It's born traveling at the cosmic speed limit and maintains that speed until it ceases to exist. This wave-particle duality isn't unique to light, by the way. It's a fundamental feature of quantum mechanics. Electrons, protons, even entire atoms exhibit the same behavior. Everything in the quantum world has this dual nature. But light was the first place where physicists truly had to grapple with this strange reality. Let's think about what a photon actually is for a moment. It has no mass. It has no electric charge. It exists as pure energy, traveling at the maximum possible speed. A photon never experiences rest. From the moment of its creation, perhaps in a hot stellar core, or in a light bulb filament, or during an atomic transition, it races through space at 299,792,458 meters per second until something absorbs it. The energy of a photon is determined by its frequency, or equivalently, its wavelength. High-frequency photons, like gamma rays, carry more energy than low-frequency photons, like radio waves. But they all travel at the same speed. Red light and blue light, despite having different wavelengths, travel at exactly the same velocity through vacuum. When light travels through a material, through glass, water, air, it slows down slightly. This happens because the photons are constantly being absorbed and re-emitted by the atoms in the material, creating a slight delay. The denser the material, the more this happens, and the slower the effective speed of light through that material. This is why light bends when it enters water or glass. The change in speed causes refraction. But in the vacuum of space, where there are no atoms to interact with, light travels at its maximum speed. This is what we mean by the speed of light, the speed in vacuum, the fundamental constant c. It's the speed at which causality propagates through the universe. Here's something curious to consider as you drift towards sleep. Every photon that has ever reached your eyes has traveled at this speed. The light from the ceiling of your room right now, the sunlight that warmed your face this morning, the light from distant galaxies that you see in astronomical photographs. All of it, every single photon, traveling at exactly the same speed. And each photon carries information. When you look at something, you're seeing it because photons bounced off it, or were emitted by it, and traveled to your eyes. The photon carries information about the object, its color, its brightness, its texture. encoded in the photon's wavelength and intensity. All of this information travels at the speed of light, neither faster nor slower. The universe is constantly being mapped by light. Every star shines in all directions, sending photons out into space. Every hot object emits infrared light. Every atom, when excited, can emit photons. And all of this light, all these photons, travel outward at the cosmic speed limit, carrying information about their sources across the void. In a sense, we're all connected by light. The photons that reach us from distant stars form a tangible connection, a physical link across the vast emptiness of space. When you see a star, photons from that star are entering your eye, depositing their energy in the cells of your retina, causing chemical reactions that your brain interprets as vision. You and that distant star are touching, in a way, through the medium of light. And this happens at the speed of light, no faster, no slower. It's the pace at which the universe reveals itself to us, the rate at which we can gather information about distant places and objects. It's a fundamental limitation, but also a fundamental gift. The universe continuously sending us messages at the maximum possible speed. Take a moment to rest your eyes. When you open them again, remember that you're seeing everything through light that has traveled to you at this cosmic speed. The walls of your room, the ceiling, your hands if you raise them, all visible because photons are constantly bouncing off these surfaces and entering your eyes at 299,792,458 meters per second. It's a small miracle, happening every moment, usually without our noticing it at all. Einstein's insight, spacetime and relativity. To truly appreciate why the speed of light is so fundamental, we need to understand Einstein's revolutionary insight about space and time. This is where physics becomes almost mystical, where our everyday intuitions about reality are gently challenged and transformed. Before Einstein, people thought of space and time as separate entities. Space was where things existed. Time was when they existed. They were independent backgrounds against which the universe played out its drama. You could measure distances in meters and durations in seconds, and these measurements would be the same for everyone, regardless of how they were moving. Einstein changed all of this with his theory of special relativity. He showed that space and time are not separate but are woven together into a single fabric called spacetime. Events don't just happen at a particular location or at a particular time. They happen at a particular point in spacetime, defined by both spatial coordinates and a time coordinate. Imagine spacetime as a vast four-dimensional tapestry. 3 dimensions of space, length, width, height, and 1 dimension of time, all interlinked. Every event, every moment in the history of the universe is a point in this tapestry. Your birth, your first day of school, this very moment as you read these words, all points in space-time, connected by the paths, objects, and light rays take through this 4-dimensional structure. The speed of light emerges as the fundamental conversion factor between space and time in this unified space-time. It tells you how much space corresponds to how much time. When we say light travels at 300,000 kilometers per second, we're essentially saying that 300,000 kilometers of space is equivalent to 1 second of time in the geometry of space-time. This might sound abstract, but it has concrete consequences. One of the most famous is time dilation, which we touched on earlier. When you move very fast, time slows down for you relative to someone who's stationary. This isn't an illusion or a malfunction of clocks. It's a real effect of moving through space-time at high velocity. Picture this gently. Imagine 2 twins. One stays on Earth. The other boards a spaceship and travels at 99% of the speed of light to a distant star system and back. The journey might take, from Earth's perspective, 20 years. But for the traveling twin, due to time dilation, only a few years might pass. The traveling twin would return younger than their sibling who stayed home. This is called the twin paradox, though it's not really a paradox, just a counterintuitive consequence of relativity. The closer you get to the speed of light, the more pronounced this effect becomes. At 99.9% of the speed of light, time slows down by a factor of about 22. At 99.99%, it's a factor of about 70. At 99.999999%, time slows down by a factor of over 2,200. The universe would age millennia while you experienced just a year. And as we discussed earlier, at exactly the speed of light, which you can't reach if you have mass, time would stop entirely. This is why photons don't experience time. From a photon's perspective, it's emitted and absorbed in the same instant. Its entire existence is a single, eternal moment stretching across however many light years it travels. Length contraction is the spatial counterpart to time dilation. When you're moving very fast, distances in your direction of motion appear contracted. A meter stick flying past you at nearly the speed of light would look shorter than a meter. A spaceship approaching at relativistic speeds would appear squashed, compressed in the direction of its motion. Again, this isn't an optical illusion. The spaceship really is shorter in that frame of reference. Space itself is contracted along the direction of motion. Different observers, moving at different speeds, literally experience different geometries of space. This leads to some mind-bending scenarios. Imagine you have a long stick and you're approaching a barn at near light speed. The barn is barely long enough to fit the stick when it's at rest. But due to length contraction, from your perspective, the barn appears much shorter than the stick. How can the stick possibly fit inside? The resolution involves carefully thinking about simultaneity. Events that appear simultaneous in one reference frame may not be simultaneous in another. The front of the stick entering the barn, the back of the stick entering the barn, and the closing of the barn doors are different events that occur at different spacetime points. Different observers, moving at different speeds, will disagree about whether these events happen at the same time. This is one of Einstein's most profound insights. There is no universal now that extends across all of space. Simultaneity is relative. Whether two events happen at the same time depends on your state of motion. The further apart two events are in space, the more different observers will disagree about whether they happen simultaneously. The speed of light is central to all of this because it's the maximum speed at which information can travel, and therefore it defines the limits of causality. If event A can cause event B, then A must occur in B's past light cone, the region of spacetime from which light could have traveled to reach B. Events outside this light cone cannot affect B, because doing so would require information to travel faster than light. Think of it like concentric ripples spreading out from a stone dropped in a pond. The ripples can only affect things they can reach. Similarly, an event can only influence things within its future light cone, the region of spacetime it can reach by sending signals at the speed of light or slower. The rest of the universe, for now, is causally disconnected from that event. This creates what we might call the texture of spacetime, a structure where some events can influence others and some cannot, all governed by the cosmic speed limit. The speed of light isn't just a velocity, it's the fundamental parameter that determines the causal structure of the universe. In Einstein's general theory of relativity, which extends special relativity to include gravity, spacetime itself can be curved by the presence of mass and energy. Massive objects like stars and planets create dips and curves in the spacetime fabric. Other objects move along the straightest possible paths through this curved spacetime, which we perceive as orbits and gravitational attraction. But even in curved spacetime, the local speed of light remains constant. If you were to measure the speed of light in your immediate vicinity, you'd always get c, regardless of how strong the gravitational field is or how curved spacetime might be. Light always travels along what are called null geodesics, the straightest possible paths through spacetime that things moving at the speed of light must follow. Near extremely dense objects like black holes, spacetime becomes so curved that strange things happen. There's a boundary called the event horizon, within which spacetime is curved so strongly that all paths lead inward. even light, traveling at its maximum speed, cannot escape. It's not that gravity pulls so hard that light can't overcome it. It's that spacetime itself is curved in such a way that there are no paths leading outward. The geometry itself traps light. Let's pause here and breathe. The speed of light is intimately connected to the structure of spacetime itself. It's the conversion factor between space and time. It's the speed at which causality propagates. It's the parameter that appears in the equations describing how spacetime curves in response to mass and energy. It's woven into the very fabric of reality. And all of this emerged from Einstein asking a simple question. What would the universe look like if the speed of light were the same for all observers? From that one question, combined with the principle that the laws of physics are the same in all inertial reference frames, the entire structure of special relativity follows. Time dilation, length contraction, the relativity of simultaneity, the equivalence of mass and energy, all of it flowing from those two simple postulates. There's something elegant about this, something almost musical. The universe has a deep mathematical structure, and the speed of light is one of its fundamental notes. When you understand relativity, you begin to see the universe not as a collection of objects moving through empty space and marching through time, but as a unified space-time continuum where everything is connected, where the geometry itself is dynamic and responsive to matter and energy, and you, lying there in the darkness, are part of this space-time tapestry. Your body exists in space, your consciousness experiences time, and these are not separate things, but aspects of a single unified reality. The photons reaching your eyes from the dim light of your room or device screen are traveling through space-time along their null geodesics, connecting you to your surroundings at the cosmic speed limit. The cosmic horizon and the limits of observation. The speed of light doesn't just limit how fast things can travel, it also limits what we can observe. Because light takes time to travel, and because the universe has a finite age, there are regions of space so distant that their light hasn't had time to reach us yet. This creates what astronomers call the observable universe. The universe began, as far as we can tell, about 13.8 billion years ago in the event we call the Big Bang. Light has been traveling through space ever since, but it's only had 13.8 billion years to travel. You might think this means the observable universe would have a radius of 13.8 billion light-years, but it's actually larger, about 46 billion light-years in radius. Why the discrepancy? Because the universe itself is expanding. While light has been traveling toward us, the space through which it travels has been stretching. Distant galaxies are receding from us, not because they're moving through space, but because space itself is expanding, carrying them along. This expansion means that light from distant objects has had to cover more ground than it would in a static universe. Think of it like drawing dots on the surface of a balloon and then inflating the balloon. The dots aren't moving across the balloon's surface, but they're getting farther apart because the surface itself is stretching. Similarly, galaxies aren't moving through space so much as being carried along by the expansion of space itself. The most distant objects we can observe are so far away that their light has been traveling toward us for most of the age of the universe. When we look at these distant galaxies, we're seeing them as they appeared billions of years ago, when the universe was young. We're literally looking back in time, observing ancient history written in light. The cosmic microwave background radiation represents the furthest back we can see. It's the glow of the universe when it was only about 380,000 years old, the moment when it became transparent to light for the first time. Before that, the universe was so hot and dense that it was opaque. A roiling plasma where photons couldn't travel freely. But when the universe cooled enough for stable atoms to form, light suddenly had a clear path, and it's been traveling toward us ever since. The light we see from the cosmic microwave background has been traveling for over 13 billion years. It's the oldest light we can observe, a faint whisper from the earliest moments of the universe, and it travels to us at the speed of light. No faster, no slower, taking billions of years to complete its journey. This creates a kind of cosmic horizon, a limit to how far we can see. Not because space ends, but because light from beyond a certain distance hasn't had time to reach us yet. There could be infinite space beyond our observable universe, filled with galaxies and stars, and potentially even life. But we can never see it because the light from those distant regions will never reach us. In fact, due to the accelerating expansion of the universe, there are galaxies we can see right now, whose light will never reach Earth in the future. The space between us and them is expanding faster than light can cross it. We're seeing them now because their light began its journey long ago. But if we tried to send a signal to them, that signal would never arrive. The expansion of space would carry those galaxies away from us faster than our signal could catch up. This is one of the profound limitations imposed by the speed of light. Not only can't we travel to these distant galaxies, we can't even communicate with them. They exist beyond our cosmic horizon, forever out of reach, moving away from us faster than the speed of light through the expansion of space itself. Does this violate the cosmic speed limit? Surprisingly, no. Remember, the speed of light limits how fast things can move through space. It doesn't limit how fast space itself can expand. The galaxies aren't moving through space faster than light, they're being carried along by the expansion of space. It's a subtle but important distinction. Imagine you're walking on a moving walkway at an airport. Your speed through the air might be 5 kilometers per hour, but if the walkway is moving at 4 kilometers per hour in the same direction, your speed relative to the ground is 9 kilometers per hour. You haven't exceeded your personal speed limit, you're just on a moving platform. Similarly, galaxies can recede from us faster than the speed of light if the space between us is expanding fast enough, even though they're not moving through space faster than light. This creates some interesting scenarios. There are regions of the universe that are receding from us so rapidly that any signal we send would never catch up. The expansion of space would carry the destination away faster than our signal could travel. These regions are, in a practical sense, unreachable. They exist in the universe, but they're beyond our cosmic horizon, separated from us by the relentless expansion of space. Let's drift for a moment on this cosmic perspective. You're lying there in your small corner of space, on a planet orbiting an average star in an unremarkable galaxy. Around you, in all directions, space extends for billions of light years. Galaxies by the hundreds of billions, each containing hundreds of billions of stars. And beyond what we can see, possibly infinite space, forever beyond our reach because the universe is expanding and light can only travel so fast. The speed of light gives the universe a kind of layered structure of accessibility. Nearby objects within our solar system are relatively accessible. We can send spacecraft there, receive signals back in hours or minutes. Nearby stars are less accessible. We'd need decades or centuries to reach them, even with impossibly fast spacecraft. Distant galaxies are essentially unreachable given any plausible technology. And beyond our cosmic horizon, regions exist that we can never observe or interact with, cut off from us by the expansion of space. This might sound lonely or isolating, but there's also something peaceful in it. The universe is vast beyond imagining. There are more stars than grains of sand on all Earth's beaches, and all of that immensity exists within its own cosmic speed limit, unfolding according to the laws of physics, with light traveling at its constant velocity, connecting distant regions through the patient, steady accumulation of photons, making their long journeys through space. When you look up at the night sky, when light conditions permit and you can see stars, you're seeing light that has traveled years, decades, centuries, or even millennia to reach your eyes. Every photon that enters your pupil has been traveling at 219,792,458 meters per second for all that time, maintaining its speed perfectly, never wavering, until it finally strikes your retina and is absorbed, transferring its tiny quantum of energy and completing its cosmic journey. And in that moment, you're connected to a distant star, to an event that happened long ago, to a corner of space billions of kilometers away. The photon bridges that distance at the maximum speed the universe allows, neither faster nor slower, carrying information across the void in the only way the universe knows how, at the speed of light. Light in different media. We've been talking about light traveling through the vacuum of space, where it moves at its maximum speed. But what happens when light travels through different materials? This is where things become practical, where the abstract constant c manifests in everyday phenomena you can observe and experience. When light enters a material, glass, water, air, even the jelly-like substance inside your eye, it slows down. Not because the photons themselves are moving slower, but because they're constantly being absorbed and re-emitted by the atoms in the material. This absorption and re-emission process creates a slight delay, making the effective speed of light through the material slower than it would be in vacuum. The amount light slows down depends on the material's refractive index. Water has a refractive index of about 1.33, meaning light travels about 1.33 times slower in water than in vacuum, or roughly 225,000 kilometers per second. Glass typically has a higher refractive index, around 1.5, so light moves even slower through glass, about 200,000 kilometers per second. Still extraordinarily fast, of course, but slower than the universal constant c. And this difference in speed is responsible for many of the optical phenomena you see every day. When light moves from one medium to another at an angle, from air into water, for example, the change in speed causes the light to bend. This is called refraction, and it's why a straw in a glass of water appears bent or broken at the surface. Imagine a car driving from a paved road onto sand at an angle. If the right wheels hit the sand first, they slow down while the left wheels are still on pavement moving at full speed. This causes the car to turn slightly toward the right. Similarly, when light enters a denser medium at an angle, it bends toward the normal, the line perpendicular to the surface. This bending is responsible for many beautiful phenomena. Rainbows form because raindrops split white light into its component colors through refraction and reflection. Different wavelengths of light bend by different amounts. Red light bends less than blue light, so the colors separate and spread out. When sunlight enters a raindrop, reflects off the back surface, and exits, the different colors emerge at slightly different angles, creating the arc of colors we call a rainbow. Lenses work by exploiting refraction. A curved piece of glass can bend light rays to focus them to a point or to spread them out. Your eyes contain lenses that focus light onto your retina. Eyeglasses correct vision by adding another lens that compensates for imperfections in your eye's natural lens. Microscopes and telescopes use carefully shaped lenses to magnify tiny objects or gather light from distant stars. All of this is possible because light slows down when traveling through transparent materials, and this slowing is wavelength dependent. It's a gentle reminder that while the speed of light in vacuum is a universal constant, light's behavior in materials is rich and variable, giving rise to much of the optical complexity we observe. There's an interesting limit to this slowing, by the way. In extremely cold, specially prepared clouds of atoms, scientists have slowed light down to absurdly slow speeds. In 1999, physicist Lena Howe and her team managed to slow light to about 17 meters per second, about 38 miles per hour, slower than highway traffic. In later experiments, they even briefly stopped light completely, trapping it in a quantum state in the atomic cloud before releasing it. These experiments work with something called a Bose-Einstein condensate, an exotic state of matter that exists at temperatures near absolute zero. The atoms in the condensate are prepared in a special way so that light interacts with them very strongly, creating the dramatic slowing effect. It's far from everyday experience, but it shows that while the fundamental speed of light in vacuum is constant, the effective speed of light in materials can vary dramatically. In everyday life, the slowdown of light in materials is subtle but important. When you look at an object underwater, it appears closer than it really is because of refraction. When you see a mirage on a hot road, you're seeing light bent by layers of air at different temperatures, creating an illusion of water. When you use a magnifying glass, you're bending light rays to make small objects appear larger. All of these phenomena rely on light changing speed as it moves between different media. And yet, in the brief moments when a photon is traveling between atoms, when it's actually moving through the empty space within and between atoms, it's still moving at c, the full, fundamental speed of light. The slowdown is statistical, a result of the absorption and re-emission process happening many times as light makes its way through the material. Think of it like walking through a crowded room. Your maximum walking speed might be 5 kilometers per hour. But if you have to stop and chat with every person you meet, your average speed across the room will be much slower. The stopping and starting doesn't change your walking speed when you're actually walking. It just reduces your average speed over the whole journey. Similarly, photons still travel at c between interactions, but the interactions themselves create an effective slowdown. This interplay between light and matter is fundamental to how we see the world. Every color you perceive, every shape, every shadow, emerges from light interacting with materials, bouncing off surfaces, passing through transparent objects, being absorbed by pigments. And all of it happens at speeds we can barely comprehend, yet slow enough that the information takes time to reach you, creating the slight lag that separates event from perception. Right now, the light reaching your eyes from this screen or page is light that was emitted milliseconds ago. Tiny fractions of a second, but not zero time. Light from the lamp on your bedside table, if you have one lit, is reaching you nanoseconds after leaving the bulb. Every photon you see is a messenger from the immediate past, traveling at the speed of light through whatever medium fills your room. And when you close your eyes, that information stream stops. The photons continue bouncing around your room, of course, reflecting off walls and furniture. But they no longer enter your eyes, no longer deposit their energy in your retinal cells. The visual connection to your surroundings is temporarily severed, leaving you in gentle darkness, guided by memory and other senses, while light continues its eternal dance all around you. Let's rest here for a moment. Feel the darkness behind your eyelids. Know that when you open your eyes again, light will stream in at hundreds of millions of meters per second, bringing you information about your surroundings in the only way the universe knows how to communicate visual information, through the propagation of electromagnetic waves at the cosmic speed limit, modified slightly by the materials through which they pass, but always fundamentally limited by c. The finite speed of light and astronomy. The finite speed of light has profound implications for astronomy and our understanding of the cosmos. Because light takes time to travel, when we look at distant objects in space, we're not seeing them as they are now. We're seeing them as they were when the light left them. We're looking back in time. The sun is about 150 million kilometers away, a distance called an astronomical unit, or AU. Light takes about 8 minutes and 20 seconds to travel this distance. This means that when you look at the sun, which you shouldn't do directly, of course, you're seeing it as it was about 8 minutes ago. If the sun suddenly vanished right now, we wouldn't know about it for over 8 minutes. We'd continue to see the sun, continue to feel its warmth, until the last photons it emitted before disappearing finally reached us. The moon is much closer, about 384,000 kilometers away. Light takes about 1.3 seconds to travel from the moon to Earth. During the Apollo missions, there was a noticeable delay in radio communications between mission control and the astronauts on the moon. They were literally talking to each other across time, with messages taking over a second to cross the distance. As we look to more distant objects, the time delays become more dramatic. Neptune, the outermost planet in our solar system, is about 4.5 billion kilometers from the Sun, or about 30 AU. Light takes over 4 hours to travel from the Sun to Neptune. If an astronomer on Neptune were observing the Sun through a telescope, they'd see the Sun as it appeared 4 hours earlier, When we move beyond our solar system, the scales become truly astronomical. The nearest star system, Alpha Centauri, is about 4.37 light-years away. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. So Alpha Centauri is about 41 trillion kilometers from us. The light we see from those stars tonight left them over 4 years ago. If an intelligent civilization lived on a planet orbiting those stars, and they looked at our sun through a powerful telescope, they'd see Earth as it was 4 years ago. This creates a strange situation where different observers in the universe have different presence. An observer on Earth sees Alpha Centauri as it was 4 years ago. An observer on Alpha Centauri sees Earth as it was 4 years ago. Neither can see the others now. The speed of light imposes this fundamental limitation on how quickly information can travel, creating a layered structure of present moments throughout space. The center of our Milky Way galaxy is about 26,000 light-years away. The light we observe from that region left when our ancestors were still living in the Stone Age, painting caves and beginning to develop agriculture. An observer at the galactic center looking at Earth with an impossible telescope would see our planet as it was 26,000 years ago, long before recorded history. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. The light entering your eye from Andromeda on a clear, dark night began its journey 2.5 million years ago, when human ancestors were just beginning to use stone tools. It has been traveling through space ever since, maintaining its constant velocity, carrying information about that distant galaxy across the vast emptiness between galaxies. Some of the most distant galaxies ever observed are over 13 billion light-years away. We're seeing them as they appeared when the universe was less than 1 billion years old, when the first galaxies were just beginning to form. These ancient photons have been traveling toward us for most of the age of the universe, crossing incomprehensible distances at the cosmic speed limit. There's something poignant about this. The light from these distant galaxies is like a message from the deep past, a postcard from the universe's youth, and we receive these messages constantly. Every clear night, photons from countless distant sources rain down on Earth, carrying information about stars and galaxies and cosmic events, all traveling at exactly the same speed, all limited by the same cosmic speed limit. This means that astronomy is, fundamentally, a historical science. We can't observe the current state of distant objects. We can only observe their past. The farther away something is, the farther back in time we're looking. Astronomers don't just study space, they study spacetime, observing events distributed not just across distance, but across time itself. This has important implications for understanding cosmic evolution. By observing galaxies at different distances, and therefore at different epochs in the universe's history, astronomers can piece together how galaxies form, evolve, and change over billions of years. It's like having a time machine, except instead of traveling back in time yourself, you're looking at light that has traveled forward in time to reach you. The cosmic microwave background, which we mentioned earlier, is the ultimate example of this. It's the oldest light we can observe, a snapshot of the universe when it was just 380,000 years old. This ancient light has been traveling for over 13 billion years to reach us, and its properties tell us about the conditions in the early universe, its temperature, its density, its composition. All of this is possible because light travels at a finite speed. If light traveled instantaneously, we'd see everything in the universe as it is right now, with no time delay. We'd lose this window into the past. The universe would appear very different. We'd have no way to study cosmic history, no way to see how things have changed over time. So the finite speed of light, far from being a limitation, is actually a gift. It allows us to observe the universe's history, to see distant galaxies as they were billions of years ago, to study the evolution of cosmic structures over time. It turns the universe into a vast archive of its own past, with light serving as the carrier of historical information. And all of this happens at 299,792,458 meters per second. Not faster, not slower. Every photon from every distant galaxy, every ancient star, every cosmic event, all traveling at this exact speed, taking as long as they need to cross the distances between there and here, between then and now. Lie back and imagine it. Right now, photons from distant stars are passing through your location in space. Photons that have been traveling for years or centuries or millennia. They're moving through the air in your room, through the walls of your house, through you yourself, carrying information about distant corners of the cosmos. Most pass by undetected. But some, the visible ones, if you were to look up at a clear night sky, enter your eyes and complete their long journey, finally depositing their energy and transmitting their message after traveling across vast stretches of space and time. The universe is constantly sending us these messages. Light from everywhere, from everything that shines, propagating outward at the cosmic speed limit, creating an intricate web of causal connections. And we sit here, in our small corner of space, receiving these messages, reading this cosmic mail, learning about the universe through the patient accumulation of photons that have traveled incomprehensible distances just to reach us. Light speed and communication. The finite speed of light doesn't just affect how we observe the universe, it also fundamentally limits how we communicate, especially across large distances. This is becoming increasingly important as humanity begins to explore the solar system and contemplates future missions to other star systems. Consider the Mars rovers, the robotic explorers we've sent to the surface of the red planet. Mars is, on average, about 225 million kilometers from Earth, though this distance varies considerably as both planets orbit the Sun. At that distance, it takes light between 3 and 22 minutes to travel between the two planets, depending on their relative positions. This means that when scientists on Earth send a command to a Mars rover, there's a minimum delay of several minutes before the rover receives the command, plus another several minutes for any response to travel back. If a rover encounters an obstacle and engineers need to give it new instructions, the total time for this round-trip communication can be 30 minutes or more. This makes real-time remote control impossible. You can't drive a Mars rover like you'd drive a remote-controlled car in your backyard. The time delay is too long. Instead, the rovers are given high-level instructions and must be somewhat autonomous, able to make simple decisions on their own and avoid obstacles without constant human guidance. As we send missions to more distant destinations, this problem becomes more severe. The New Horizons spacecraft, which flew by Pluto in 2015, was about 5 billion kilometers from Earth at the time of its closest approach. Radio signals took over 4.5 hours to reach the spacecraft from Earth, and another 4.5 hours for any response to come back. The total round-trip communication time was over 9 hours. Imagine trying to have a conversation where each exchange takes 9 hours. You ask a question. 9 hours later, you get an answer. You respond. 9 hours later, you receive a reply. It's not really a conversation anymore. It's more like exchanging very slow letters, where the postal service happens to travel at the speed of light. This is the reality of communicating across solar system distances. The speed of light is fast, extraordinarily fast. But space is so vast that even at this cosmic speed limit, communication takes significant time. And the problem only gets worse when we consider interstellar distances. The nearest star system, Alpha Centauri, is 4.37 light-years away. A radio message sent from Earth to a hypothetical planet orbiting those stars would take 4.37 years to arrive. If someone there immediately sent a reply, we'd receive it 4.37 years later. The total round-trip communication time would be 8.74 years. You could send a message as a child and receive the reply as a teenager. This means that any kind of interactive communication with other star systems is essentially impossible. The time delays are simply too long. The best we could do would be to send information-rich messages and hope someone eventually receives them and chooses to respond. It would be a conversation spanning decades or centuries, carried out at the maximum speed the universe allows, the speed of light, but still constrained by the vast distances between stars. SETI, the search for extraterrestrial intelligence, operates with this understanding. Radio telescopes scan the sky looking for artificial signals from other civilizations, but researchers know that any signal they detect will be ancient. If we detected a signal from a civilization 1,000 light years away, we'd be receiving a transmission that was sent 1,000 years ago. By the time we compose and send a reply, 1,000 more years would pass before they received it. The civilization that sent the original message might not even exist anymore by the time our reply arrived. This creates a strange, lonely situation. The speed of light ensures that any communication between stars is necessarily historical. You can never have a conversation with someone in another star system. You can only exchange messages with their past and they with yours. The now of a distant civilization and the now of Earth are forever separated by light travel time. Even on Earth, the finite speed of light creates small delays. When you make an internet video call to someone on the other side of the world, from New York to Sydney, for instance, the signal must travel about 16,000 kilometers through fiber optic cables. Light travels slower in fiber optic cable than in vacuum, about 200,000 kilometers per second. So the signal takes about 80 milliseconds to make the journey, creating a small but noticeable delay in the conversation. Satellite internet connections have even longer delays because the signals must travel up to satellites in orbit and back down, a total distance of tens of thousands of kilometers. This is why satellite internet connections often feel slightly laggy. You're experiencing the finite speed of light in action. High-frequency stock trading systems are designed to minimize these light travel delays. Trading companies place their servers as close as possible to stock exchange servers, sometimes even laying special fiber optic cables along the most direct routes possible between cities. A few milliseconds of advantage, a few milliseconds of light travel time saved, can be worth millions of dollars. They're literally competing against the speed of light, trying to shave off every possible nanosecond of communication time. These might seem like exotic examples, but they illustrate a fundamental principle. Information cannot travel faster than light. This isn't a technological limitation that we might overcome with better engineering. It's a fundamental feature of the universe. Cause and effect are limited by the speed of light. Communication is limited by the speed of light. The spread of influence, the propagation of knowledge, the transmission of data, all of it flows at the cosmic speed limit, no faster. In a sense, the speed of light defines the pace of events in the universe. It determines how quickly things can happen, how quickly information can propagate, how quickly one event can influence another. It's the universal clock rate, the tempo at which causality unfolds. Take a moment to appreciate this. Every message you've ever sent online, every phone call you've made, every piece of information you've shared has traveled at speeds ultimately limited by the speed of light. The signals may have been electrical currents in wires or radio waves through air or light pulses in fiber optic cables, but all of them were constrained by this fundamental limit. None of them could travel faster than approximately 300,000 kilometers per second. When you talk to someone standing next to you, sound waves carry your voice at about 343 meters per second, much slower than light. But the visual information, the light reflecting off their face, allowing you to see their expressions, reaches you at the speed of light. When you're having a conversation, you're actually experiencing the person's appearance slightly ahead of their words, though the difference is so small, microseconds, that you never notice. Everything you perceive, every sense you have, relies on information traveling at finite speeds. Sound is slow, smell is slower, molecules drifting through air at walking pace. Touch is relatively quick, nerve signals traveling at tens or hundreds of meters per second. But nothing exceeds the speed of light. It's the universe's ultimate speed limit for the transmission of information. And this creates the texture of your experience, the slight delay between event and perception, the fact that you're always experiencing the immediate past, not the present. When you look at your hands, you're seeing them as they were nanoseconds ago, When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you look at distant stars, you're seeing them as they were years or centuries ago. You are, in a sense, embedded in a web of light signals, all traveling toward you at the cosmic speed limit, carrying information about your surroundings. This web creates your visual experience of reality, stitched together from countless photons that have traveled from sources near and far, all moving at exactly the same fundamental velocity. As you drift towards sleep, imagine these light signals converging on you from all directions. Photons from nearby objects arriving in nanoseconds. Radio waves from distant transmitters taking fractions of a second. Light from stars taking years or centuries. All of it flowing toward you at the speed of light, creating the informational structure of your experience, limited and defined by this fundamental cosmic constant. The nature of photons. Let's return now to the photon itself, the quantum of light, the particle that embodies electromagnetic radiation. Understanding photons more deeply helps us appreciate why they travel at the speed they do and what it means for something to have no mass yet carry energy and momentum. A photon is a strange entity. It has no mass, no electric charge, no physical size in any conventional sense. It's a packet of energy, a quantum of electromagnetic field. It exists as a pure excitation of the electromagnetic field that permeates all of space. When an atom transitions from a higher energy state to a lower one, it releases this energy in the form of a photon, a discrete bundle of electromagnetic energy that propagates through space at the speed of light. The energy of a photon is proportional to its frequency. High-frequency photons, like X-rays and gamma rays, carry more energy than low-frequency photons, like radio waves. This relationship is described by Planck's equation, E, hf, where E is energy, h is Planck's constant, a fundamental constant of nature, and f is frequency. Different frequencies of light correspond to different colors for visible light, or different types of electromagnetic radiation more generally. Red light has a lower frequency than blue light, so red photons carry less energy than blue photons. Infrared photons carry even less energy, while ultraviolet photons carry more. But all photons, regardless of their energy or frequency, travel at exactly the same speed in vacuum, the speed of light, c. A low-energy radio wave photon races through space at the same velocity as a high-energy gamma-ray photon. They differ in energy and frequency, but not in speed. This is quite different from massive particles. If you throw a baseball and a bowling ball with the same energy, the lighter baseball will move faster than the heavier bowling ball. Massive particles can have different speeds depending on their mass and energy. But photons all travel at the same speed, the cosmic speed limit, because they have no mass at all. Why does having no mass mean traveling at the speed of light? This emerges from Einstein's special relativity. The relationship between energy, momentum, and mass is described by the equation E2 equals pc2 2 plus mc22, where E is energy, P is momentum, m is mass, and c is the speed of light. For a particle with mass, there's a contribution from both the momentum term and the mass term. But for a photon, where m equals 0, the equation simplifies to E equals pc, meaning all of a photon's energy comes from its momentum. The speed of a particle is related to its energy and momentum. For a massless particle like a photon, this relationship forces the particle to travel at exactly c. It can't travel slower. That would be inconsistent with having zero mass. It can't travel faster. That would violate causality. It must travel at exactly the speed of light. This means that photons are born moving at c and die moving at c. They never accelerate. They never decelerate. From the moment of their creation to the moment of their annihilation, they travel at this constant fundamental velocity. There's something almost noble about this, a particle that knows only one speed, the maximum speed allowed by the universe, and maintains it perfectly throughout its existence. The lifetime of a photon can vary dramatically. Some photons exist for only nanoseconds, traveling microscopic distances before being absorbed. Others travel for billions of years across intergalactic space, carrying information about distant galaxies across cosmic distances before finally being absorbed by a telescope mirror or detector. During this journey, the photon doesn't experience time. From a photon's perspective, if we can even speak of such a thing, its emission and absorption happen simultaneously. The entire journey, whether it's a nanosecond across a room or a billion years across space, is a single, eternal instant. This is one of the strange consequences of time dilation at the speed of light. Time stops. The journey is instantaneous. For us, watching from outside, the photon's journey takes time, sometimes vast amounts of time. But for the photon itself, traveling at sea, time doesn't pass. It exists in a kind of frozen instant, a moment that stretches across whatever distance it travels, but contains no duration. Photons also have a property called spin, which is a kind of intrinsic angular momentum. Unlike massive particles, which can have various spin values, photons have a spin of 1 in units of Planck's constant divided by 2p. This spin can point in different directions relative to the photon's direction of motion, corresponding to different polarizations of the light. Polarization is the orientation of the electric field oscillation in an electromagnetic wave. Light can be polarized vertically, horizontally, circularly, or at various angles. Polarizing sunglasses work by filtering out certain polarizations of light, reducing glare from reflected surfaces. LCD screens use polarizers to control which pixels appear bright and which appear dark. When a photon is absorbed, all of its energy is transferred to whatever absorbs it. The photon ceases to exist. Its energy might excite an electron to a higher energy level, or create heat by increasing molecular vibrations, or trigger a chemical reaction in a camera sensor or in the cells of your retina. But the photon itself is gone. It's not diminished or scattered. It's completely absorbed, converted from a quantum of electromagnetic energy into other forms of energy in the absorbing material. This absorption and emission process is happening constantly all around you. Atoms in your surroundings are absorbing photons and emitting new ones. The light you see reflecting off walls is actually new light. Photons absorbed by the wall material and new photons emitted in response. The wall doesn't just bounce the same photons back. It absorbs them and creates new ones. Even your body is doing this constantly. You emit infrared radiation, heat, which means atoms in your body are emitting infrared photons. About 100 watts of power, the same as a bright light bulb, is radiated from your body in the form of infrared photons. These photons stream off your skin, traveling at the speed of light until they're absorbed by your clothing, the air, or nearby surfaces. At night, in the darkness, you are a glowing beacon of infrared light. If someone could see infrared radiation, they'd see you shining gently, emitting photons in all directions. You're a source of light, just like the sun or a star, though at much lower energy and intensity. And all of these photons you emit travel away from you at exactly c, carrying away your body heat, distributing your thermal energy into your environment. Let's rest here for a moment. Close your eyes and imagine the photons streaming off your body, racing away at 300,000 kilometers per second, carrying microscopic amounts of energy, but doing so constantly, billions upon billions of photons every second, creating your thermal signature in the universe. You are not just a receiver of light, you are also an emitter, a gentle source of electromagnetic radiation, participating in the constant exchange of photons that fills the universe. Section 11. Light as information. Perhaps the most profound role that light plays is as a carrier of information. Everything you know about the world beyond your immediate touch comes to you through photons, light particles that carry encoded information about their sources and about everything they've interacted with along their journey. When you look at something, photons bouncing off that object enter your eyes. These photons carry information encoded in their wavelength, which you perceive as color, their intensity, which you perceive as brightness, and their arrival time, which helps you perceive motion. Your brain processes this flood of photons, millions of them every second hitting your retinas, and constructs a rich, detailed visual representation of your surroundings. This is information transmission at the speed of light. The information about an object's color, shape, texture, and position travels from the object to your eyes at 299,792,458 meters per second. There's a brief delay, nanoseconds for nearby objects, but this is so short that your brain can't detect it. From your perspective, vision seems instantaneous, even though it's actually limited by the finite speed of light. Cameras work on the same principle. When you take a photograph, you're collecting photons that carry information about the scene. Each photon hitting the camera sensor deposits its energy, contributing to the electrical signal that forms the image. The resulting photograph is a record of photons, a capture of light that traveled at the cosmic speed limit from the scene to the sensor. All modern communication technology relies on encoding information into light or radio waves, which are also electromagnetic radiation, just at different frequencies than visible light. When you stream a video, watch television, talk on a cell phone, or browse the internet, information is being encoded into electromagnetic waves and transmitted at the speed of light, or slightly slower if traveling through cables or fiber optics. Fiber optic cables, which form the backbone of the internet, transmit information as pulses of light. A laser at one end of the fiber produces rapid flashes of light encoding digital information, ones and zeros. These light pulses travel through the optical fiber at about 200,000 kilometers per second, slowed slightly from c due to the refractive index of the glass, carrying data from place to place. A single optical fiber can carry enormous amounts of information. Modern systems can transmit terabits per second, trillions of bits of information every second, all encoded in light pulses racing through the fiber. The data for thousands of phone calls, hundreds of video streams, millions of web pages, all flowing simultaneously through a strand of glass thinner than a human hair, all at speeds approaching the speed of light. Radio communication works similarly. When a radio station broadcasts, it encodes audio information into radio waves, electromagnetic radiation at much lower frequencies than visible light. These radio waves propagate through the air at the speed of light, carrying the encoded information to any radio receiver tuned to the right frequency. The same principle applies to television broadcasts, cell phone signals, Wi-Fi, Bluetooth, GPS satellites, all forms of wireless communication. Information is encoded into electromagnetic waves and transmitted at the speed of light. The radio waves carrying your phone call move at the same fundamental speed as the visible light entering your eyes, all limited by the same cosmic constant. This creates an interesting connection between information theory and physics. Information cannot travel faster than light. This isn't just a practical limitation, it's a fundamental feature of the universe. The speed of light is the maximum speed at which any information can be transmitted, the upper limit on how quickly one event can causally influence another. This has implications for computing as well. The speed of light limits how quickly different parts of a computer can communicate with each other. Modern computer processors are so fast that the time it takes for signals to travel from one part of the chip to another, literally the time light takes to cross a few centimeters, becomes a significant limitation. Computer engineers have to carefully design processors to minimize these light travel delays. They place components that need to communicate frequently as close together as possible. They use multiple levels of caching to keep frequently accessed data nearby. They design parallel processing systems that work on different parts of a problem simultaneously, minimizing the need for communication. In a sense, the speed of light determines the clock rate of the universe. It sets a fundamental limit on how quickly things can happen, how quickly information can flow, how quickly complex systems can process and respond. No matter how advanced our technology becomes, we'll always be constrained by this limit. Information cannot travel faster than c. This connects back to our earlier discussion of causality. Information is what allows cause and effect to work. For event A to cause event B, information about A must reach the location of B. This information can travel at most at the speed of light. Therefore, causality itself is limited by the speed of light. It's a deeply fundamental connection between information, causality, and the structure of spacetime. When you see a star in the night sky, photons from that star are delivering information to you. Information about the star's temperature, encoded in the spectrum of light. Its brightness, encoded in the intensity. Its chemical composition, encoded in absorption lines in its spectrum. Its motion, encoded in Doppler shifts of those spectral lines. All of this information travels to you at the speed of light, taking years or centuries to complete its journey. And you, receiving these photons, are the endpoint of an information transmission that began long ago and far away. The photon carries its information faithfully across the void, maintaining its properties, delivering its message about a distant source. When it finally reaches your eye or a telescope detector, that information is extracted, processed, and becomes part of our collective knowledge about the universe. Every observation in astronomy is an act of information reception. The telescope doesn't see stars, it collects photons carrying information about stars. The astronomer doesn't observe distant galaxies. They analyze information delivered by photons that have traveled for billions of years. All of our knowledge about the cosmos beyond our immediate vicinity comes from photons, light particles that carry information at the cosmic speed limit. In your everyday life, you're constantly receiving and interpreting information carried by photons. The text you're reading now reaches you through light. The faces of people you see are visible because of light. The beauty of a sunset, the color of flowers, the shape of clouds, all visual information transmitted to you by photons traveling at 299,792,458 meters per second. You are, in a very real sense, connected to your environment through a constant stream of photons. They arrive from all directions, carrying information about your surroundings, updating your perception many times per second. This stream of information creates your visual experience of reality, constructed from the data carried by light particles traveling at the maximum speed allowed by the laws of physics. As you prepare for sleep, this stream of visual information begins to diminish. You close your eyes, the room darkens or is already dark. The constant input of light-carried information slows to a trickle or stops entirely. Your consciousness, freed from the need to process visual data, can drift into other modes of thought and eventually into sleep. But even then, even with your eyes closed in a dark room, photons continue their eternal dance around you. Infrared photons from warm surfaces, radio waves from distant transmitters, the faint glow of electronic devices, light from outside filtering through curtains. The universe continues its constant transmission of information through light, even when you're not receiving it, even when you're not aware of it. And in the morning, when you open your eyes, the information stream will resume. Photons will flood into your eyes once again, carrying fresh information about your surroundings, all traveling at that same cosmic speed, rebuilding your visual world after the gentle absence of sleep. The constancy of light speed and its implications. One of the most remarkable things about the speed of light is that it's constant, truly constant. It doesn't change based on the motion of the source or the observer. It doesn't change based on the direction of travel. It's always the same value, 299,792,458 meters per second in vacuum. This constancy is so counterintuitive that it took humanity thousands of years to discover it, and when Einstein proposed it as a postulate of special relativity, many physicists initially found it hard to accept. It violates our everyday experience of how velocities work. Imagine you're on a train moving at 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour relative to the train. From the perspective of someone standing still on the platform, the ball is moving at 150 kilometers per hour, the sum of the train's speed and the ball's speed. Velocities add in a simple, intuitive way. But light doesn't work like this. If you're on a spaceship moving at half the speed of light, and you shine a flashlight forward, you might expect the light to be moving at 1.5 times the speed of light, half c from your motion plus c from the light itself. But this doesn't happen. The light still travels at exactly c. An observer watching from a stationary position would measure the light moving at c, not 1.5 c. You, on the spaceship, would also measure it moving at c relative to you. How can this possibly be? How can light have the same speed for everyone, regardless of their relative motion? The answer is that space and time adjust to preserve the constancy of the speed of light. As you move faster, time slows down for you and distances contract in your direction of motion, in exactly the right way to ensure that light still travels at c from your perspective. This constancy has been verified in countless experiments. Particle accelerators routinely accelerate particles to speeds exceeding 99.99% of the speed of light. These particles emit light as they move. If light speed added to the particle speed, we'd detect light moving faster than c. But we never do. The light still travels at exactly c, no matter how fast the source is moving. Michelson and Morley, in their famous 1887 experiment, tried to detect changes in the speed of light due to Earth's motion through space. They reasoned that if Earth was moving through some medium that carried light waves, the hypothetical luminiferous ether, then light should travel faster or slower depending on whether it was moving with or against Earth's motion through this medium. They built an incredibly sensitive instrument called an interferometer that could detect tiny differences in light travel times. They measured the speed of light in different directions at different times of year, when Earth was moving in different directions in its orbit around the Sun. And they found nothing. No variation. Light traveled at the same speed, regardless of direction or time of year. This null result was deeply puzzling at the time. It seemed to suggest that Earth was always at rest with respect to the ether, which was implausible. Or perhaps the ether didn't exist at all. But if there was no ether, what was light waving through? Einstein's solution was elegant. Light doesn't need a medium. It's a self-propagating wave of electric and magnetic fields, and it travels at a constant speed, c, in all reference frames. There is no preferred reference frame. There is no ether. There's just space-time, and light traveling through it at a speed that all observers measure to be the same. This constancy is so fundamental that, as we mentioned earlier, we now define the meter in terms of it. We've essentially declared light travels at exactly 299,792,458 meters per second by definition. A meter is however far light travels in 1 times 299,792,458 of a second. This makes the speed of light an exact value with no measurement uncertainty. The constancy of light speed has another interesting implication. It provides an absolute speed limit. In Newtonian physics, velocities could theoretically be unlimited. You could keep accelerating indefinitely, going faster and faster without bound. But relativity shows that as you approach the speed of light, it becomes progressively harder to accelerate further. The speed of light becomes an asymptote, a limit you can approach but never reach if you have mass. This creates what we might call the relativity barrier. Objects with mass can reach 90% of light speed, 99% of light speed, 99.999% of light speed, and so on, but they can never quite reach 100%. It would take infinite energy. The speed of light stands as an eternal barrier, forever keeping massive objects below this fundamental limit. Only massless particles can reach this speed. And for massless particles, it's not a limit they can reach. It's the only speed they can have. Photons don't accelerate to the speed of light. They're created moving at the speed of light. They can't move slower or faster. The speed of light is their natural, inevitable velocity. There's something beautiful in this dichotomy. Massive particles can have any speed below c, but can never reach c. Massless particles can only move at c, and can never move at any other speed. The speed of light divides reality into two categories: things that have mass and move slower than light, and things that don't have mass and move at the speed of light. There's no middle ground. This constancy also means that the speed of light is universal. It's the same everywhere in the universe, at all times, in all directions. A photon traveling through intergalactic space, far from any stars or galaxies, moves at exactly the same speed as a photon in your room. The age of the universe doesn't matter. The local density of matter doesn't matter. The cosmic expansion doesn't matter. Light always travels at c. This universality makes the speed of light one of nature's true constants, a number built into the fabric of reality itself, unchanging across space and time. It's as fundamental as the existence of space and time themselves. You can't have the universe we inhabit without the speed of light being what it is. Physicists sometimes wonder, could the speed of light have been different? Could the universe have had a different value for c? Theoretically, perhaps, but such a universe would be dramatically different from ours. The relationships between energy, momentum, mass, and velocity would all change. The structure of space-time would be different. Atoms might not be stable. Stars might not shine. The universe might not be hospitable to life at all. We live in a universe where the speed of light is approximately 300,000 kilometers per second, and this value has profound consequences for everything that exists. It's not just a speed limit on motion. It's a fundamental parameter that shapes the structure of reality, determining how space and time relate to each other, how matter and energy behave, how causality works, how the universe evolves. Let's rest with this thought. The speed of light, constant, universal, fundamental, is woven through every aspect of physical reality. It appears in equations describing electricity and magnetism. It appears in equations describing matter and energy. It appears in equations describing space and time. It's not just a measured quantity. It's a defining feature of the cosmos we inhabit. And right now, in this moment, light is traveling past you, through you, around you, all moving at this same constant velocity. Photons from every direction, carrying energy and information, all obeying the same fundamental rule. Thou shalt travel at c, no faster, no slower, forever and always. It's a cosmic speed limit, yes, but more than that, it's a fundamental organizing principle of reality itself. Section 13. Exotic phenomena and light speed. While the speed of light is constant and represents an ultimate limit, there are some exotic phenomena in physics that seem to allow for faster-than-light speeds or other strange behaviors. Let's explore a few of these gently, understanding both what they appear to be and what they actually mean within the framework of modern physics. One intriguing phenomenon is quantum entanglement. When two particles become entangled, measuring a property of one particle instantly determines the corresponding property of the other, no matter how far apart they are. Change the state of one, and the other responds immediately, or so it seems. This spooky action at a distance, as Einstein called it, appears to involve faster-than-light communication between the particles. However, and this is crucial, you can't actually use entanglement to send information faster than light. The correlations between entangled particles are real and instantaneous, but they don't allow for controllable signaling. When you measure one particle, you get a random result. The other particle will have a correlated result, but since your result was random, you can't encode a message in it. The correlation exists, but no information travels faster than light. Think of it like this. Imagine two magic coins that always land on opposite faces. You flip yours in New York and get heads. Instantly, you know that someone flipping the paired coin in Tokyo will get tails, but you can't control whether you get heads or tails. It's random. So you can't send a message. The correlation is there, but causality isn't violated. Information still can't travel faster than c. Another interesting phenomenon is Cherenkov radiation. When a charged particle moves through a medium faster than light can travel through that medium, it produces a characteristic blue glow called Cherenkov radiation. This is the source of the eerie blue glow you sometimes see in photographs of nuclear reactors. But this isn't really faster than light travel in the problematic sense. Remember, light slows down in materials. In water, light travels at about 225,000 kilometers per second. A high-energy particle can move faster than this speed through water, while still moving slower than the fundamental speed limit, c. The particle is moving faster than light in water, but not faster than light in vacuum. It's like running past a snail. You're faster than the snail, but you're not breaking the human speed limit. Phase velocity is another apparent faster-than-light phenomenon. In certain situations, the phase velocity of a wave, the speed at which peaks and troughs of the wave appear to move, can exceed c. For instance, in waveguides or certain optical systems, phase velocities exceeding the speed of light are possible. However, phase velocity doesn't represent the speed at which information or energy travels. That's given by the group velocity, which is the speed at which wave packets or pulses move. And the group velocity never exceeds c. The phase velocity is more of a mathematical artifact than a physical speed. It's like watching the point where the blades of a pair of scissors meet moving along the blade. This point can move faster than either blade is moving, but it's not a physical object carrying energy or information. There are also quantum tunneling scenarios, where particles seem to move through barriers faster than light could cross the barrier. In these cases, the particle has a probability of appearing on the other side of a barrier, even though it doesn't have enough energy to climb over it classically. Time measurements of this tunneling process sometimes suggest faster than light speeds. But again, careful analysis shows that no information travels faster than c. The quantum wave function of the particle extends beyond the barrier, and the measurement process collapses this wave function, making it appear as if the particle traversed the barrier in no time. But you can't use this to send signals or information faster than light. The process is fundamentally quantum and doesn't allow for controlled information transmission. Wormholes and warp drives are theoretical concepts from general relativity that might, in principle, allow for effective faster-than-light travel. A wormhole would be a tunnel through space-time, connecting two distant points. You'd enter at one end and emerge at the other, potentially crossing vast distances in a short time. A warp drive would manipulate space-time around a spacecraft, contracting space ahead and expanding it behind, allowing the ship to effectively move faster than light without actually moving through space faster than c. These ideas are mathematically consistent with general relativity, but they require exotic matter with negative energy density, something we've never observed and aren't sure even exists. They also raise causality problems, potentially allowing for time travel to the past and the paradoxes that entails. Most physicists suspect that some principle we don't yet understand prevents these exotic space-time configurations from actually occurring in nature. Even if wormholes or warp drives were possible, they wouldn't involve anything actually moving through space faster than c locally. The light speed limit would still apply to local motion. It's just that space-time itself would be manipulated to create shortcuts or allow for effective faster-than-light travel without violating local physics. The expansion of the universe provides another case where things appear to move apart faster than light. Distant galaxies are receding from us at speeds that, due to the expansion of space itself, can exceed the speed of light. But again, this isn't motion through space. It's the expansion of space carrying them along. The galaxies themselves aren't moving through space faster than c. The space between us and them is growing, and this growth has no speed limit. These examples illustrate an important point. The prohibition against faster-than-light travel is specifically about motion through space and the transmission of information or causality. It's deeply connected to the structure of spacetime and the principle that cause must precede effect. Various apparent violations, upon careful examination, turn out not to violate these fundamental principles after all. The speed of light remains the ultimate speed limit for anything carrying information or causality. It's a robust limit, woven into the fundamental structure of physics. While exotic scenarios might create apparent exceptions, they don't provide loopholes for sending signals or traveling faster than light in any way that would violate causality. This is reassuring in a way. The universe has rules, deep mathematical principles that govern how things work. These rules are self-consistent and don't have loopholes that would lead to paradoxes or contradictions. The speed of light is one of these rules, and despite decades of theoretical and experimental work, it stands firm as a fundamental limit. As you lie there in the darkness, contemplating these exotic phenomena, remember that they're all happening within the framework of a universe governed by consistent rules. Quantum entanglement creates correlations but not faster than light signaling. Particles can tunnel through barriers but not faster than c. Space can expand faster than light, but objects can't move through space that fast. The cosmic speed limit remains inviolate, protecting the causal structure of spacetime, ensuring that the universe remains logically consistent. That cause always precedes effect, that time flows in one direction. There's something deeply peaceful in this consistency. The universe isn't arbitrary or chaotic. It follows rules, deep, mathematical, elegant rules that have held since the beginning of time and will continue to hold until the end. And the speed of light is one of these fundamental rules, as basic to reality as the existence of space and time themselves. Philosophical reflections on light speed. As we near the end of our gentle journey through the nature of light and its speed, let's take a moment to reflect on what all of this means more philosophically. The speed of light isn't just a scientific fact. It's a profound statement about the nature of reality itself. In a sense, the speed of light defines the texture of the universe. It determines how quickly events can unfold, how rapidly information can spread, how fast cause and effect can propagate. It creates a fundamental pace to reality, a cosmic tempo that everything must follow. Nothing can move faster. Nothing can communicate faster. Nothing can influence distant events faster than this fundamental limit allows. This creates a certain loneliness to existence. Each point in space is isolated from distant points by light travel time. You can never know what's happening right now at a distant location. You can only know what was happening there in the past, when the light you're now receiving began its journey. The present moment, the cosmic now, is fundamentally local. It extends only as far as light can travel in an instant, which is to say, only to your immediate vicinity. The further away something is, the more the when of its existence is separated from your now. When you look at the sun, you see it as it was 8 minutes ago. When you look at Alpha Centauri, you see it as it was over 4 years ago. When you look at the Andromeda Galaxy, you see it as it was 2.5 million years ago. Each of these objects exists in its own now, separate from yours, accessible to you only through the ancient light that has traveled across space at the cosmic speed limit. There's something poignant about this. The universe is vast and filled with countless objects and events, but each observer can only experience a small subset of cosmic history, the past light cone of their current location. Everything beyond this cone is either in the future or causally disconnected. The speed of light creates boundaries around what can be known, what can be experienced, what can be interacted with. And yet, there's also something connecting about light. Every photon that reaches your eyes forms a tangible link to its source. When you see a star, photons from that star are physically interacting with molecules in your retina. You and that distant star are touching, in a sense, across the void. The light bridges the distance, connects you to faraway places and times, brings information from across the cosmos to your consciousness. The speed of light also highlights the interconnectedness of space and time. They're not separate entities, but aspects of a unified space-time continuum. The speed of light is the conversion factor between them, telling you how much space corresponds to how much time. Move through space quickly, and you move through time slowly. Move through space at the maximum rate, the speed of light, and you don't move through time at all. This suggests that space and time are, in some deep sense, the same kind of thing. They're different dimensions of the same underlying structure. The speed of light is the parameter that relates them, that shows how they transform into each other, depending on your motion. It's a bridge between space and time, a fundamental connection that reveals their unity. From a philosophical perspective, the constancy of the speed of light is remarkable. In a universe where so much changes, stars are born and die, galaxies collide and merge, the cosmos expands and evolves, the speed of light remains constant. It's the same everywhere, at all times, for all observers. It's a true universal constant, unchanging and eternal. This constancy provides a kind of anchor in the ever-changing universe. No matter what happens, no matter how the cosmos evolves, light will always travel at sea. This constant becomes a foundation on which other understanding can be built. It's a reliable, unchanging feature of reality that we can depend on, that will be the same tomorrow as it is today, that was the same in the distant past as it is now. The finite speed of light also means that the universe has a history. If light traveled instantaneously, we'd see everything as it is right now. There would be no looking back in time, no window into cosmic history. But because light takes time to travel, we can observe the past. We can see galaxies as they appeared billions of years ago. We can study the evolution of the universe by looking at objects at different distances. In this sense, the finite speed of light is a gift. It gives us access to cosmic history that would otherwise be lost. It allows us to be not just observers of the present, but students of the past, learning about how the universe has changed and evolved over billions of years. The universe becomes a vast library of its own history, with light serving as the carrier of historical information. There's also something democratic about the speed of light. It's the same for everyone, regardless of their motion, regardless of their location, regardless of their technology. A photon in your room travels at the same speed as a photon in the heart of a distant quasar. An observer moving at half the speed of light measures the same light speed as an observer at rest. Rich or poor, human or alien, near or far, everyone measures the same value for c. This universality suggests that the speed of light is truly fundamental, built into the structure of reality itself, rather than being an arbitrary parameter that could have been different. It's not a historical accident or a contingent feature of our particular universe. It's a necessary consequence of how space-time works, how causality functions, how the universe is structured at its most basic level. As you prepare for sleep, contemplating the speed of light and all it implies, consider this. You are part of this universe, subject to its rules, connected to distant places by the light that travels between here and there. You exist in space-time, experiencing the flow of time and the extension of space as unified aspects of a single reality. You receive information carried by photons traveling at the cosmic speed limit, and you emit information in the form of thermal radiation traveling at that same speed. You are not separate from the universe. You are embedded in it, part of its fabric, participating in its constant exchange of energy and information. The speed of light that governs distant galaxies also governs the photons bouncing off your skin, the light entering your eyes, the electromagnetic radiation your body emits. You are subject to the same fundamental limits as everything else, connected to the cosmos through these deep, universal principles. And there's something comforting in that. You're not isolated or alone. You're part of a vast, interconnected universe where everything follows the same rules, where light travels at the same speed everywhere, where cause and effect propagate according to universal principles. You're a small part of something much larger, something beautiful and elegant and governed by mathematical laws that have held since the beginning of time. As your eyes grow heavy and consciousness begins to fade, remember that the universe continues its eternal dance around you. light continues to propagate at sea. Photons continue their journeys across space. Information continues to flow at the maximum speed the cosmos allows. And you, resting there in the gentle darkness, are part of all of this. A conscious observer in a universe of light and matter, space and time. All governed by elegant rules, all connected by the fundamental constant we call the speed of light. Part 3. Closing sequence. What is the speed of light? It's the question that brought us here, whispered softly at the beginning, like a child asking how fast light can race across the universe. And after wandering through measurements and relativity, photons and spacetime, causality and information, we find ourselves gently circling back to where we began, still wondering. We've learned that light travels at approximately 300,000 kilometers per second, fast enough to circle the Earth 7.5 times in the blink of an eye. We've explored how scientists measured this, seemingly, immeasurable speed, from Römer observing Jupiter's moons to modern lasers spanning continents. We've discovered that this speed is not just a velocity, but a fundamental constant woven into the very fabric of spacetime itself. We've seen how the speed of light creates a cosmic speed limit, how nothing with mass can reach this velocity, how photons are born traveling at sea and maintain it until they're absorbed. We've understood that this speed limit is intimately connected to causality, ensuring that cause always precedes effect, that information cannot travel faster than light, that the universe maintains its logical consistency. Maybe the speed of light doesn't have to make intuitive sense on human scales. Maybe it just is. A fundamental feature of reality that operates beyond our everyday experience. Maybe that's the whole point. The universe doesn't need to conform to human intuitions. It simply unfolds according to laws we're only beginning to understand. Laws that include the constancy and universality of the speed of light as a cornerstone principle. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though if I was, well, at least you've learned a few things about light, speed, spacetime, and the fundamental constants that govern our universe along the way. And if you're already halfway to sleep, may your thoughts be filled with softly racing photons and gently expanding spacetime. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perhaps a physics student pondering these mysteries? Or someone who just finds the speed of light strangely relaxing? And did any particular part of this journey resonate with you? The historical measurements, the philosophical implications, or perhaps the strangeness of photons that don't experience time? If you found this gentle journey into the speed of light relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of physics, astronomy, and beyond. Each like, each subscription helps this little corner of the internet grow and reach more people seeking peaceful education and restful learning. Thank you for joining me on this exploration of light's cosmic speed limit. Sleep well, dream deep, and may your consciousness drift at speeds far below the universal maximum into realms of rest and restoration. Remember, every photon you've ever seen has traveled at exactly this same speed, 299,792,458 meters per second, neither faster nor slower, connecting you to your surroundings and to the distant cosmos through the patient, steady propagation of light. Good night.